hear me?
Yes, sir.
Yeah. We can recollect what we were discussing in the previous session. We spoke about the resistors. The three major types of resistors we were discussing, we were speaking about. What are the three main types of resistors? I had given you an assignment also. Some of you have sent the assignment. A few of you have not sent it yet. Can you respond, please? Jovian, Edwin, Zaid, Aditya. I just want you to get back to whatever we were discussing so that we will be able to continue. Yeah, carbon resistors. That's good. Yeah, carbon film and wire bond resistors. The differences between these three types, are you clear? Do you have any doubts on them? Yes, that's good, Rania. And Zaid, you have responded. Carbon film, wire bond resistors. The three categories. Carbon resistors are generally used resistors, general type resistors with normal tolerance levels of 5%, 10%, and sometimes 20% also. Metal film resistors, they are high accuracy resistors, precision resistors. They are wire bond resistors. Generally, they are of low ohmic value, low resistance values, used for high power applications. So these are the three types of resistors that we were discussing. Exam point of view, again I keep asking you on the exam point of view. They can ask about these three types of resistors. You will have to answer giving the details and maybe even the figures that we were discussing in the previous session. What else we initiated? We started speaking about the color coding, and I had given you assignment also. As I was telling, a few of you have sent assignments. Few of you still they have not submitted. Please submit it. They will be counted for assignments for internals by your class teacher. So even though there is a delay, I want to submit them. Maybe in future I will be asked to stick on to the time given. As of now, whatever assignments I had given you in the previous sessions, please work out on all those assignments and submit. This is for the ones who have not submitted the assignments. Right, back to the session here. We were discussing about color codes. I have scanned through a few of the assignments submitted by you all, and based on that I felt yes, I had to take it a little more in detail. So I will be continuing with the color coding of resistors today. Shall we go on?
Yes, sir.
Yeah, once again, very happy new year. So this is the 4-bar color code that we had discussed. We had initiated the discussions, and you people are already clear about the 10 different colors that are there. The BB Roy of Great Britain, very great wife or a very good wife. BB black, brown, RO white, red, orange, yellow. GB green and blue, and then violet, grey, and white. These are the 10 standard colors that are used for color coding purposes. We do use other two colors, gold and silver. Generally, they are used as multipliers or for indicating the tolerances. They are not generally used for indicating the colors or for the value of the resistors. This is the basic chart, and these are the basic values, the colors that you should remember throughout. And I was mentioning that these color codes are used even in other places. I can say these are internationally accepted color coding values. Black stands for 0, brown for 1, red for 2, orange for 3, and so on, and white for 9. Many places, even in cables, when they use on the computers or equipment with different types of cables, when they are using multiple wires, they use this color codes. For resistors, this is the method that they are following to identify the color codes. The 4-band color coding, the first band represents the first digit, second band represents the second digit, third band is a multiplier. In a 4-band color code, the third band will be a multiplier, fourth one will be the tolerance. To distinguish the 3 bands, you may have to look at this particular gap, the direction of reading the color codes. You should not read it this way. My arrow, you please see, you should not read it the other way. That is, the first band is not brown. Brown is the fourth band. You can see there is some gap here between the 3 bands and the fourth band. Or all the bands will be onto one side with the complete gap the other side. So you will have to read from left to right. So the typical example, because there is a video also, you will be able to see that. I will show. Typical example of a 4-band is this. First band is red, second band is black, third band is green. After the gap, the fourth band is silver. For the second band, they have given the value 2. Red is 2, black is 0, and then green is 5. The multiplier is powers of 10. So 2, 0 into 10 to the power of 5 is the value. That is 2 megohms. When we shorten it into the standard powers of 10, the value will be 2 megohms. And since it has silver as the fourth or the tolerance band, the tolerance here would be 10%. So the value of the resistor having this color code will be 2 megohms plus or minus 10%. Sometimes, as you can see, the fourth band would be missing. This we were discussing the previous class also. I am showing it in the pictorial way. First, second, and third band, the same like the previous slide. Fourth band is removed. In such a case, the value remains the same, the tolerance is higher. When there is no band present, that indicates the tolerance as 20%. A bit of understanding of the tolerance. When we say 20% tolerance, the value as, let's say in this example, 1 kilo ohm plus or
Sir,
minus 20%. Yes,
sir, I am not able to see the slide.
you are not able to see the slide. How about others?
That's also I think.
Yeah, how about others? Let me see. Can you
Yes, sir.
re-log in? Others, are you able to see?
Sir, we cannot. No one can see, sir.
No one is able to see. 1 second. Are you able to see this slide? That's the basic
No,
stat
sir.
slide.
No, sir.
No, sir. No, sir. No, sir.
Nothing.
No, sir, nothing.
1
Blank.
second, 1 second. I think. Yeah, how about now?
Okay, sir. Now it's
Yes,
visible.
sir.
Okay, okay. I think the share screen had switched off. You could hear me, right? Okay, I see the previous slide. This is the slide which I started. So the previous session. Hello? Yes, this was the slide that I started with 4 band. I was explaining the slide, the 4 different color codes, the values for them, and the way they are used. In a typical 4 band, the first band is this, second band is here, third band is here, and the tolerance band is the last one. Typical value, typical color coding of the resistor looks like this. The color codes are from left to right. You will have to read the colors from the left to right. So, in this example, you can see red, black, green, and silver. They are the 4 colors that were discussed. Red stands for 2, black is 0, green is 5, 5 is the multiplier here, so powers of 10, the third band. Fourth is silver, silver has got a 10% tolerance value. So this is the 4 band resistor which has got a value of 20 into 10 power 5, that is 20 to 10 to power 5 or 2 megohms. When there is no fourth band, there will be only 3 bands. They are very low tolerance resistors, I can say low accuracy resistors. The example is shown here. There is no fourth band. In such a case, you can see the tolerance you will have to take it as 20%. I was trying to explain you about the tolerance. In this example, it is 1 kilo ohm plus minus 20% since there is no band. How we apply the tolerance, I was trying to explain. On 1 kilo ohms, when we say 20%, the tolerance, it will be 20% of 1 kilo ohm. For easy understanding, 1 kilo ohm is 1000 ohms. So 20% of 1000 is 200 ohms. So this particular resistor having this color coding without the fourth band can have a value anywhere between 1000 ohms plus or minus 200 ohms. That is from 800 ohms to 1200 ohms or 0.8 kilo ohm to 1.2 kilo ohm in this particular case. That is how we apply the tolerance plus or minus 20% when we say. On this value, the 20% of this value will be applying. The value can be anywhere between that. When you measure the actual value of the resistor using an ohm meter or a multimeter, it can show anywhere between 800 to 1200 ohms in this particular case. That is how we apply the tolerances. You may get problems on this also. Indicate the values of the resistor. Not just indicating the color code. Along with that, you will have to tell the resistor band of value that the resistor can have. So you will have to add one more line here to put in the value. The value can vary between 800 ohms and 1200 ohms in this example. Is it clear? Right, we'll go to the fifth band, 5-band code. Everything is similar except that we have 3 digits for the 5-band resistor. Here you have got in the 3-band or the 4-band, you have got 2 for the digits. The third is a multiplier. Whereas the difference is in a 5-band resistor, first 3 bands are for the digits. The 4th band will be the multiplier, 5th band will be the tolerance. The rest, everything remains the same. You need to apply the color codes for all these things, considering first, second and third band as the digits. We'll see with an example. For a 6th band, again, it's like a 5-band resistor. There is a 6th band also. The 5th band will represent the tolerance. The 6th band will represent what we call as temperature coefficient of resistance. That is, variation of the resistance with temperature. In very high temperature sensitive applications, we will have to be very much concerned about the variation of resistors in the circuits, in the electronic boards in the circuits. The resistors that are used, wherein the application is very highly temperature sensitive, such places these resistors must be very stable. They should not change the resistance values with temperature. So in such places we will be using very highly stable resistors against temperature, and such resistors will be having 6 bands. The 6th band will indicate the value of the temperature coefficient of resistance. TCR stands for temperature coefficient of resistance. 100. This is in ppm per degree Kelvin. The unit of temperature coefficient of resistance represented by these color bands is in terms of ppm, that is parts per million. When we say per ppm, it's parts per million. Million is 10 lakhs. So 1 in 10 lakhs. Percentage, when we say 1% means that is 1 in 100. 2% is 2 in 100. Likewise, ppm is much smaller value, parts per million. 1 in 1 million. If you say 1 part per million, it is 1 in 1 million, 10 lakhs rather. So in this case, brown stands for 100 ppm. That is, the variation of this resistance can be 100 in 10 lakhs for every degree change. Let's say if the value 10 lakhs is 1 megohm, okay, 1 followed by 6 zeros, 1 megohm, that 1 megohm for every degree change, it can vary by 100 ohms. You get the point? For every degree temperature change in kelvins, the variation of the resistor having a brown band would be 100 parts per million. So if you take the example of 1 megohm is 10 lakhs. If you consider that this particular resistor having a brown band as its 6th band can vary its resistance apart from the tolerance. It can change its resistance by 100 ohms for every degree Kelvin change in temperature. If it has red as the 6th band, the same variation will be 50 ohms per megohm. Similarly, if it is violet, it is 5 ohms per megohm. A very highly stable resistor having a violet band. We can go with that. That will be the understanding. Could you follow me so far? Is my explanation giving you clear differences? Again, why I am explaining this is you need to learn to apply tolerances and you need to know the ppm, parts per million, in your professional life also. You will come across these things in many other places, particularly since you are onto the medical field, P&O. Your representation many places would be errors or counts would be in ppm. Most of the times it may not be in percentage values, it can be in ppm. Right? We'll go with the example next. In the 6-band resistor, you can see this is the type of a resistor that would be there. 1, 2, 3 the digits, 4th is the multiplier, 5th is the tolerance, 6th is the TCR, temperature coefficient of the resistance. In this case, you can see there is a brown band here. This brown band as the 6th band, as I discussed with you earlier, what it is, it stands for 100 parts per million. The variation would be 100 parts in a million. Right? This is the standard in a single sheet, single slide, the different color codes, the different bands that are applied along with this. You can see the 4-band resistor, 5-band resistor, 6-band resistor, and what they represent. You can see in the 4-band resistor, first band represents this one, first digit, second digit, third digit is, you can see the arrow here, the line here, it is representing the multiplier. In a 4-band or 5-band resistor, first digit, second digit, third digit, fourth digit is the multiplier. 6-band, the same like 5 bands, the 4th band here, 5th band here, and 5th band here would represent the tolerance. That is what it is shown here. 6th band, temperature coefficient is in the last line. The values are also given. A ready reference for you. Keep this handy, note it down. I would suggest draw it in your notebook also, because exam point of view, you can get problems. They will give the color codes and ask you to tell the value. Sometimes they'll ask you to, they'll give the value of the resistor and ask you to write the color codes for the resistor. Both ways it is possible, so you must be very conversant on these things. Don't make mistakes. What I have seen in my past experience is, students, they make mistake here, black and brown. They get confused, they mix it up. For brown, they'll say 0. Many times I have seen, they say brown as 0, they take it as 0, and black, they take it as 1. Such mistake should not be done. Be careful. When it comes to the tolerances, they are slightly erratic. The figures are not the same way as these standard colors represent. Silver tolerance is 10%, gold is 5%. Going by the number 5 is small number, silver is bigger number. Gold, any resistor having a gold band in the tolerance band is a better resistor. Better stability, better accuracy as compared to the one which has got silver band. But when you look into it, there is this 4th band, if it's a brown band, it is even better. If it's green, it's still better. If it's violet, it's the best probably, going by the color codes. If this particular band is a violet color band, that will be one of the highly accurate resistors. So keep that in mind. Right? We just see a small video. It's not small, of course, it has got every explanation in a pictorial manner also. Please go through it and then we will continue discussions. Can you hear the sound?
Yes, sir.
sir.
We'll continue with the video.
Hey friends, welcome to the YouTube channel All About Electronics. So in the previous video, we have seen the different types of resistors. Now the value of this resistor is usually defined using the
See, this
color
front
codes.
resistor,
And in fact, you might have observed the different color bands painted on the.
these are the four actual resistor, the way it looks, and the color codes. Green, blue, orange, and then gold.
Resistor. So now let us find out in this video how to find the value of this resistor from this color codes. Now the commercially available resistors can have either 4, 5 or 6 bands, and depending upon the number of color bands, these resistors are known as either 4 band, 5 band or 6 band resistors. So now first of all, let us find out how to find the value of these 4 band resistors. So if you see any 4 band resistor, then you will find the 4 color bands, and out of the 4 color bands, the first 2 bands defines the first 2 digit of the value of the resistor. Then the third band defines the multiplying factor for this resistor, and the fourth band defines the tolerance value for the resistor. Now depending upon the color of this color band, the value of this resistor will change. So now let us find out the relationship between the color and the value that is represented by that particular color. So here is a table which defines the relationship between the different colors and the value that is represented by that particular color. So as you can see over here, the first 2 columns of this table defines the first 2 color band of this resistor, and depending upon the color of these color bands, the value that is represented by these 2 digits will change. Similarly, the next 2 columns defines the multiplying factor as well as the tolerance value for this resistor, and depending upon the color of these color bands, these 2 parameters will also change. So let us take one example so that it will get clear to you. So here we have one 4 band resistor, and if you observe over here, the first 2 color bands of this resistor are red and black respectively. So this red color band represents the value of 2, while this black color band represents the value of 0. Similarly over here, the third color band is of green color, so it represents the multiplying factor of 10 to the power 5, and the fourth band or the tolerance band over here is of silver color, so it represents the tolerance value of 10%. So now if we combine all these 4 values, then we will get the value of this resistor as 20 into 10 to the power 5, and with tolerance we can represent the value of this resistance as 2 mega ohm plus minus 10% of tolerance. So in this way, using these color bands, we can find the value of this resistor. So let us take one more example and let us find out the value of the resistor for that given color bands. So if you observe this resistor, the first 2 color band of this resistor are brown and black respectively. So this brown color band represents the value of 1, while the black color band represents the value of 0. Similarly over here, the third color band is of red color, so it represents the multiplying factor of 10 to the power 2, while here the fourth band or the tolerance band is of gold color, so it represents the tolerance value of 5%. So let us once again combine all these 4 values and let us find out the value of the resistor. So if we combine all these 4 different values, then the value of the resistor will be equal to 10 into 10 to the power 2 ohm, that is equal to 1 kilo ohm. And if we include the tolerance, then we can say that the value of the resistor will be equal to 1 kilo ohm plus minus 5%.
See, in this case, 5% gold is the tolerance. The value of this resistor, 1 kilo ohm is 1000 ohms. 5% of 1000 is 50 ohms. So the value of this resistor can be 1 kilo ohm plus or minus 50 ohms. That is, the value can range between 950 ohms to 1050 ohms. In the previous example which I explained, which is there in the next continuing video, it is 1 kilo ohm plus minus 20%. The value would range between 800 and 1200. Please watch that.
Now sometimes in this 4 band resistor, you might find that the fourth band or the tolerance band is missing. So in that case, it represents the tolerance value of 20%. So for the given example, if the fourth band is missing, then the value of the resistor R will be equal to 1 kilo ohm. And because there is a no tolerance band, it represents the tolerance value of 20%. So the value of the resistance R will be equal to 1 kilo ohm with a tolerance value of 20%. So similarly, now let us find out how to find the value of the resistor in case when it has a 5 color bands. So in case of this 5 band resistor, the first 3 color bands defines the first 3 digit of the value of the resistor, and the fourth band defines the multiplying factor for this resistor, and the fifth band defines the tolerance value for this resistor. So here is the table for this 5 band resistor, which defines the value of each digit as well as the multiplying factor and the tolerance value depending upon the color of these color bands. So let us take one example of this 5 band resistor and let us find out the value of that 5 band resistor. So here we have one 5 band resistor, and for this 5 band resistor the first color band is of red color, so it defines the value of 2. Similarly, the second color band of this resistor is of black color, so it defines the value of 0. And likewise, the third color band of this resistor is of green color, so it represents the value of 5. So here the fourth color band is of orange color, and it defines the multiplying factor of 10 to the power 3. Now the last band or the fifth band defines the tolerance value for this resistor, and it is of silver color, so it represents the tolerance value of 10%. So if we combine all these different values, then the total value of this resistor will be equal to 205 into 10 to the power 3. And with tolerance, we can say that the value of this resistor R will be equal to 205 kilo ohm with a tolerance value of 10%. So in this way, we can find the value of this resistor in case of this 5 band resistor. Now usually these 5 band resistors are used when we require the more accuracy. So similarly, now let us find out how to find the value of the resistor in case it has a 6 color bands. So these 6 band resistors are not generally used in general purpose applications, but they are used for specific applications and in military applications. So in this 6 band resistor, the first 3 color bands defines the first 3 digit of the value of the resistor, and then the fourth band represents the multiplying factor for this resistor. Then here the fifth band represents the tolerance value for the resistor, and then the last color band defines the temperature coefficient of resistance for the resistor. So here is a table from which we can find the value of the individual digits as well as the value of the multiplying factor. So depending upon the color of the color band, we can find the value of the individual digits, and from the last two columns we can find the value of the tolerance as well as the temperature coefficient of resistance for the given resistor. So let us take one example and let us find out how to find the value of this 6 band resistor. So here we have one 6 band resistor, and if you observe this resistor, here the first band of this resistor is of orange color, so basically it defines the value of 3. Then if you move to the next color band, then it is of yellow color, so it defines the value of 4. Likewise, the third color band over here is of green color, and it defines the value of 5. Now if you move to the next color band, it is of brown color, and it defines the multiplying factor of 10. So from this we can say that the value of the resistor is equal to 345 into 10 to the power 1. So if we move to the next color band, from this we can find the value of the tolerance, and over here the fifth color band is of violet color, so it represents the tolerance value of 0.1%. And then if you move to the last color band, then it is of brown color, so it defines that the temperature coefficient of resistance for the given resistor is 100 ppm per degree Kelvin. So now let us combine the individual values, and from this let us find the value of the resistor. So if we combine all these values, then we can say that the value of this resistor R is equal to 3.45 kilo ohm with a tolerance of 0.1%, and the temperature coefficient of resistance for the given resistor is 100 ppm per degree Kelvin.
See the way the value is represented in a 6 band resistor. In bracket they are giving the value also if they want to represent it. If you get a problem in the exam, you will have to represent the value in this way. Please note it down.
So in this way we can find the value of the resistor in case it has a 6 color bands. So I hope in this video you understood how to find the value of the resistor from the given color bands. So if you have any question or suggestion, do let me know in the comment section below. If you
Was it clear? You can expect one or the other question on this topic. Types of resistors, color coding of resistors, or as 3-mark questions, values of resistors also. As I mentioned earlier, they can give you a value, ask you to give the color code, or sometimes they'll give the color code and ask you to give the value. You should be very careful while you are answering. And they're very easy, so very easy that if you are clear on these color bands, those 3 marks or 5 marks will be very easy to score. So keep this handy with you. Right? We'll continue further. We start looking into the connection of individual resistors. The way the resistors could be connected. We can connect the resistors either in series or parallel. This topic, of course, we are dealing with resistors in particular now. We can connect any of the components also in series or parallel. How to deal with that? This will become the basic understanding for you. Any component we can connect. If at all they are connected in series or parallel, what is the connection? How does it look like? And how to deal with them? When we say resistors are connected in series, as seen in the figure here, we have 3 resistors, R1, R2 and R3, R1, R2, R3 connected in long chains. Other connected to the next resistor, like that. So that will be series connection. So the defining characteristic of a series circuit is that there is only one path for electrons to flow, or only one path for the current to flow. There is a single current. If we cannot apply Kirchhoff's current law here, there is no node, there is only a loop here. The current is flowing as shown in the direction in these arrows, only one direction, and single current is flowing through all the 3 resistors. The same current will be flowing through all the 3 resistors in a series combination. How to know the values in log? Typical resistance in the circuit representation, it will be like this. The same thing, we have removed this 2 ends and we have put them in a single line. That's all. This is the thing. So the total resistance in such a series circuit is equal to the sum of all the resistors in the circuit. So if you see here, R1 plus R2 plus R3 etc. plus Rn, if they are connected in series, the equivalent resistance will be R1 plus R2 plus R3 plus R4 etc. up to Rn. All of the individual values will have to be summed up. Typical example here you can see 10 ohm resistor R1, 5 ohm R2, 15 ohm R3. In this particular combination, the total resistance would be 10 plus 5 plus 15, that is 30 ohms. If you want to apply, let's say, Ohm's law, I want you to calculate the current. To calculate the current in this circuit, if the voltage is 30 volts, the voltage is 30 volts in this circuit, what would be the current flowing in this circuit? Quickly calculate and then respond back. I want you to work it out now, quickly. It's a very simple circuit, very simple value. Applying Ohm's law, what will be the current flowing in this particular circuit? 1 ampere, beautiful. Nitla has answered it quickly. Others? I equal to V by R, Ohm's law, typical Ohm's law, application of Ohm's law into this circuit. V is 30 ohms, R is the total resistance we'll have to consider. So 1 ampere current will be flowing through this circuit. If this is 30 volts, 1 ampere current will be flowing. If it is 15 volts, how much it will be? What will be the current flowing? Actually, you responded as 2 amperes. Half ampere. How about others? Yeah, 0.5 amperes actually. Aditya also is doing 0.5 amperes. Typical, going by Nejla's example. Okay. In a hurry, suddenly see what she did. If the same thing happens in the exam, a small mistake can lose 3 marks. This kind of a thing can be a 3-mark question. Instead of 1 by 2, she told 2 initially. I just gave a clue to her. She reworked it. But in the exam, you will not get that clue. Whatever you write will be final. You need to be cautious there. You should have presence of mind. Good Najla, this particular thing that you made a mistake and then corrected. For everyone, please be aware of such things that can happen. Right? So hope things are clear on the series connection of resistors. We look into the parallel connections. Now you can see the diagram. It is here. The same resistors are connected in this fashion. Now you can follow my arrows. 2 ends of the resistors are connected together. Individual ends are connected together. In the first case, in the series connection, one end is connected to the other end of the resistor, and the other end of that resistor is connected to the third resistor, and that way it keeps on going. You are clear? There is one path from 8 to 7, 2 to 1. Here you can see there are 3 different paths for the current to flow. In the previous example, the current was able to flow in only one direction. Now, the same current can flow in 3 directions. This is 1, this is 2nd, this is 3rd. So, the same current will be flowing in 3 directions. So, the total current is from here, total current gets distributed to this particular circuit. One current, second current distributes here, third current gets distributed here. They all rejoin here, and the total current is returned back. So these are in terms of nodes. You can see there are 3 nodes, currents flowing into these 3 particular points. Example, we'll just see parallel. The equivalent resistance value is 1 by R equivalent. It is not, you know, it is a summation, but the question is in parallel connections, the equivalent resistance, the reciprocal of the equivalent resistance is equal to the sum of the reciprocals of the individual resistors. When we say reciprocal, it is 1 by R1, 1 by R2, 1 by Rn. And reciprocal of the equivalent resistance is 1 by R equivalent. Many a times we make this mistake. R equivalent, we'll consider it as R equivalent equal to 1 by R1, R1 by R2, etc. Earlier students, they have been making this mistake. Be careful. It is 1 by R equivalent is equal to 1 by R1 plus 1 by R2. It is not R equivalent equal to 1 by R1 plus 1 by R2. I am repeatedly telling that. This common mistake, it's a very common mistake that's done by students. They lose marks. Typical example over here with the same values that I had discussed earlier. If R1 is 10 ohms, R2 is 5 ohms, and R3 is 15 ohms, total equivalent resistance of this circuit at this end, when you look at this end, looking from this end, is 1 by 10 plus 1 by 5 plus 1 by 15. The reciprocal of these things, 1 by 10 ohms, 5 ohms and 15 ohms. It is this value. The reciprocal is 1 over 1 by 10 is 0.1, 1 by 5 is 0.2 and 1 by 15 is 0.067. So both the three combined added together as reciprocals, 1 divided by 0.1 plus 0.2 plus 0.067, that is 0.367. 1 by 0.367 will work out to 2.725 ohms. Applying the same fashion, I want you to work out and tell me a very simple question. If all the three values are 30 ohms, 30 ohms and 30 ohms. Please work out and let me know. Ten ohms. Do you accept? Everyone else? Yeah, it's good. You are understanding it in a much better way. That's nice to see that. You should be careful. It is not 30 ohms. It is 10 ohms. 1 by 30 plus 1 by 30 plus 1 by 30 equal to 1 by R equivalent. Right? That is the way we should think of. Hope it is clear so far. Now we will look into the series and parallel combination. Possible. In electronic circuits, this particular thing is very much possible and we keep using this regularly. Here in this case, we have two loops for electrons to flow. In the previous only parallel case, it was 3 loops. Here we have got 2 loops. One loop is this, the other loop is this. Get it? One from 6, 5 to 1 and the other one is 6, 5, 4, 3 to 1. Notice how both currents go through R1 from point 2 to 1. That means here this current also flows through this resistor and this current also is flowing through this resistor. So the current that is flowing through this resistor will be the sum of these two currents that are flowing here. So here we need to apply both Kirchhoff's voltage law and Kirchhoff's current law can be applied. Kirchhoff's current law to identify the currents, individual currents flowing through these nodes. Kirchhoff's voltage law flowing to identify the individual currents once we simplify this circuit. How we do? We convert this particular combination of these two parallel resistors. We convert it to single resistor by applying the parallel combination equation. And then we apply the series combination equation to the equivalent of this resistor in series with this resistor. R1 plus R equivalent. This R equivalent will be the parallel combination of R2 and R3. That is how we apply. In this particular example which I have given, if R1 is 10 ohms, R2 is 30, and R3 is 60, what could be the value of the total resistance here? My question is this. Can you work out and write back? You need to apply series and parallel combination. For these two, you must apply parallel combination, and then the resultant will be the series combination for this. How much would be the value? Quickly just work out and take back. Ikla has told 30 ohms. Very quick in calculating. How about others? Is it right or wrong? I want to know. So the equivalent resistance R total, the total resistance would be, by the time others calculate, I'll just try to explain again. Total resistance will be R equivalent equal to R1 plus 1 over R2 and 1 over R3. Will give you 1 over R equivalent here. Get it? So R equivalent will be reciprocal of that. R1 plus 1 over 1 by R1 plus 1 by R2. That's the calculation. If you want to put it in the equation terms. Otherwise, calculate these two separately. Whatever value comes, add it up with this. That's what I have tried to give it here. Resistor network, there is a combination of parallel and series connections, can be broken up into smaller parts that are either series or parallel. So we need to break them to simpler circuits. Then only we'll be able to work it out. How about others? Have you calculated the values? Nejla has responded telling that it is 30 ohms. Another way to quickly remember this or calculations is, if they are in series, here, the resistance will be summation. Let's say in parallel circuits, if we have the same value of resistors, the resultant equivalent will be just the division by the number of resistors. For example, if say like this is 30 ohms, 30 ohms and 30 ohms, R1 is 30, R2 is 30, R3 is 30, the resultant will be 30 divided by, there are 3 resistors, divided by 3. So it is 10 ohms. 60 divided by 3, 20 ohms will be the equivalent resistance. If there are only 2 resistors in parallel, both are 40 each, 40 ohms and 40 ohms, the resultant would be 40 divided by 2, that is 20 ohms. In a different way to remember that. Whereas in the series combination, if these are 40 and 40, the series combination would be 80 ohms, 40 plus 40. This you can do easily if the value of the resistors are the same. Let's say if there are 4 resistors in parallel, like this, only one more circuit here, and each is 40 ohms, let's say, 40, 40, 40 and 40. The resultant would be 40 by 4, that is 10 ohms again. That is the way you can always remember. And one more point for you to cross-check or verify your answer would be resistors in series. I repeat, resistors in series, the equivalent resistance will be more than the value of the individual resistors. I repeat, in series circuit, the equivalent resistor, the answer that you get will be larger, will be higher than the value of the individual resistors. These are 10, 5 and 15. The previous example, if you take 10 plus 5 plus 15 is 30, and that 30 is higher than all the 3 individual resistors. 15 is the highest value here, but 30 is your answer. But in this case, if you see 10 plus 5 plus 15 in parallel combination, it will be lower than the lowest value of the resistance. In this parallel combination, the resultant resistance value will be lower than the lowest value. So the resultant will have to be smaller than the individual resistance values. In this case, you can see the smallest value resistor is 5 ohms, whereas equivalent resistance is 2.725 ohms. Smaller than this value. In series, it was bigger than the biggest value. In parallel, it is smaller than the smallest value. That's a verification checkpoint for you. Are you okay with this? So far, any doubts? Color codes, series and series and parallel combination of resistors. How about others? Are you please comfortable? Exam point of view, all these topics are quite important. Yeah, we'll go further. Different application of resistors, different types of resistors, we'll try to have a look. I will not be covering every resistor, every type of resistor that's available in the market today or that is used. A few of them I will be touching. Basically focusing on the syllabus also, because a few more additions are there considering your applications, EAU applications also. So one type of resistor which is called a thermistor. As the name suggests, thermistor has got something to do with the temperature, thermal. Okay, what it is? It's a type of resistor whose resistance is dependent on temperature, that is, changes with temperature. When we were discussing the color codes, we were discussing about the stability of the resistance with changes in temperature. Here, deliberately we will be looking into a resistance which changes a lot with temperature. And such an application is called a thermistor. A resistor whose value changes a lot with change in temperature is the one that is practically required, and that is called as a thermistor. In such applications, we will be using thermistors. The word thermistor is a combination of thermal and resistor, as I have mentioned it was. A small explanation on this, assuming the relationship between resistance and temperature is linear. It may not be linear every time, but if you assume that it is linear, change in resistance delta R is proportional, I'll put it, as a constant. The temperature coefficient of resistance is that into delta T. Delta T is change in temperature. The constant is called the temperature coefficient of resistance. So change in the resistance delta R equal to K into delta T. So the variation of this resistance is proportional to the variation of temperature. Such a case, that is called a thermistor. Where they are used? They are only used in current limiter circuits, temperature sensors, self-resetting overcurrent protectors, and self-regulating heating elements. These are a few applications of this thermistor. Again, academic point of view, what is a thermistor? Can be a question. We have to tell it's a resistance which is varying with temperature. Equation, change in the resistance is delta R equal to K into delta T, and where K is the temperature coefficient of resistance. This you'll have to bring out in the answer, and typical examples or applications where they are used. So going by the principle of operation, they can be of two types. If K is positive, that's variation of resistance with temperature. Increasing temperature, the resistance increases, K is positive. If K is positive, the resistance increases with increasing temperature. And the device is called a positive temperature coefficient thermistor. That thermistor is called a PTC, positive temperature coefficient thermistor, or a positor. On the other way, there are resistors possible wherein the resistance will decrease with increase in temperature. The resistance decreases here with increase in temperature. That is also possible. There are materials which behave in this fashion. Such of those materials, when they are used, they result in thermistors, and such thermistors are called negative temperature coefficient thermistors, NTC. Two types of thermistors. So question answer kind, what is a thermistor? At 5 marks levels, let's say, define the temperature in the thermistor, give the equation, explain the individual components of the equation, typical applications, and the types of thermistors that are there. Is it clear? Going back to the earlier discussion, resistors that are not thermistors are designed to have a K as close to 0 as possible. If K is as close to 0 as possible, that means apply 0 here. Anything multiplied by 0 is a 0. So delta R will be 0 with whatever the temperature is. That is how we analyze. The delta R is variation of resistance. If temperature coefficient of resistance is 0, the material chosen has a 0 temperature coefficient of resistance, then irrespective of the temperature, 0 into any temperature change is still 0. So delta R will remain 0. So the variation of resistance value from its original value remains constant. There is no variation. Such resistors are called highly stable resistors against temperature, so that the resistance remains nearly constant over a wide temperature range. That is the thing that is possible as applications and concepts of thermistors. Do you get clearly what a thermistor is? How about others? See, these are few topics wherein you should have good conceptual understanding. Concepts you must understand clearly. Once you are good with these concepts, no, you can apply these concepts anywhere and everywhere. Even in other components, any changes also what you see. And the crude application can be in a thermometer. The digital thermometers that you use today, they can use these kind of thermistors also inside. They will be using different circuits to process the changes in resistance with temperature, and that is converted to digital integration. A typical digital thermometer also can use. I don't say it uses this itself because it depends on the accuracy of the thermometer and the range, the temperature range at which we will be using the thermometer. For low temperature range, we may have to use different materials. For high temperatures, we may have to use different materials. That is the thing which will be seeing something more. Right, we'll see next point. Of course, as a conceptual understanding, I'm just bringing this, though it is not directly related to resistors. A thermocouple, the behavior of a thermocouple, how it works. This is for your conceptual understanding. Discussion on this. What's a thermocouple? It's an electrical device consisting of two different conductors. Please remember, the thermocouple consists of two different conductors, two different materials, two different metals, forming an electrical junction. And those junctions are at different temperatures. You see the diagram? Chromel, alumel. There are two different materials. This is one place, a reference point where they are joined together, and the other place they are kept at two different temperatures. So when we are looking at this circuit, this is the junction point which is kept in the temperature being measured. This will be the reference temperature point, and this will give the indication. This is a meter. How it works? The thermocouple, you would have heard of Joule-Thomson effect, if at all, otherwise don't worry much. What happens is, temperature dependent. A thermocouple produces a temperature dependent voltage as a result of the thermoelectric effect. This voltage can be interpreted to measure temperature. What happens here is, when materials of two different types are joined together, and that is subject to one temperature, and the other ends are subject to another temperature. Like this is in the bath, let's say this is dipped in the hot water bath or hot oil bath or a furnace, wherever this junction point is dipped or kept inside one end of the junction. The other end there are two free wires, open ends. And if at these open ends, what happens is, in such a situation, conceptually, there is a voltage, a small voltage that is getting generated. Thermoelectric effect is that. Variation in temperature, there is a small voltage that is generated. And that small change in voltage is measured using a very sensitive voltmeter and converted to read the difference in temperature between these two places. Voltage generated at a single junction of two different types of wires is used to measure temperature at very high and low temperatures. This particular application is at very high or very low temperatures. Whether the voltage depends on the type of wires used, chromel, alumel or any other wire that is used. For temperature measurements, thermocouples are self-powered. They do not require extra power, extra additional power source. They don't require any other source here. Main limitation with thermocouples is the accuracy. In this case, system errors of less than 1 degree Celsius can be difficult to achieve. That means to say, changes in temperature between this end and this end, if it is less than 1 degree, the output, the voltage that is generated by this kind of a system is so low that it is very difficult to measure or differentiate. That is the main limitation of thermocouples. So when we use this thermocouples, or where we use this thermocouple is when we have a very wide temperature variation range and we are required to focus at a particular band of temperature, not throughout. And that band should be a large band, not a very small band, very close accuracy band. It's not in terms of 1 or 2 degrees, it should be in 10, 20, 30 degrees kind, the temperature band. In such a place, we can use the thermocouple. K-type thermocouple, that is Cromwell aluminum. The material used here is Cromwell aluminum. This is the standard thermocouple configuration. The measure voltage V can be used to calculate temperature, and that's what I explained. This slide gives the information about thermocouple. These kind of devices are predominantly used in high temperature, as it's already indicated, in high temperature, very low temperature ranges. Typical example is in aircraft. Since I am from the aircraft industry, we use it in the aircraft to measure the engine temperature. It can be of the order of several hundreds of degrees, 800 degrees, 900 degrees, 600 degrees, like that, the temperature of the engine. We need to monitor closely the temperature of the engine, which indirectly is a measure of the performance of the engine. Typical applications I have put in this slide. Temperature measurement in kilns, brick burning places, gas turbine exhaust, that's what I was trying to tell you. Diesel engines. So the temperature measurement is possible in engines. It can be used even in automobiles. They are also using known this as temperature sensors in thermostats, air conditioners, any other heating appliance, in the refrigerator also. This can be applied. I don't say they are the main items. This is one type of a device that could be used in these areas. They are also find use as flame sensors and safety devices for gas powered major appliances. And they are powered by gas. Any changes, any temperature beyond a certain limit can lead to a fire hazard, accidents. Such places also they use these thermocouples. They will closely monitor the using the thermocouple, convert it back to voltage, and when the voltage is going to set limit, they will trigger protection mechanisms. That is what the meaning of a safety device or typical application of a safety device. Some clarity, we get clarity of a thermocouple and a thermistor. Can you get the difference between thermocouple and thermistor? What is a thermistor? Please be clear on the conceptual understanding of both of these two. Thermistor is a single material. The material is having the property wherein the resistance changes with temperature. Whereas thermocouple is a two material device, two metal device. Thermistor is a single metal device or single material device where the material is specific and that material temperature varies with, the resistance varies with temperature. Here, thermocouple, there are two materials, the junction is kept in one temperature, the other three ends are kept in the reference temperature. The change in temperature at the junction is measured, and that measurement is through the voltage that gets generated because of this change in temperature in two dissimilar metals or materials. The difference between the two you should be very clear. Right? Our notes prepared with the differences. Again, exam point of view, quite important. They can ask you the difference between thermistor and thermocouple also, or typical application of thermocouples, thermistor, etc. Are you clear? Right? We'll go to the next topic. Another type, resistance temperature detectors, popularly known as RTDs, what they are. They are also called resistance thermometers, as sensors used to measure temperature by correlating the resistance of the RTD element to temperature. More or less like a thermistor. Typical material is platinum, nickel or copper. How it is made? Similar to the thermistor, the metal has a predictable change in resistance as the temperature changes, and it is this predictable change that is used to determine the temperature. Typical application of thermistor concept is in the RTD. Common RTD sensing elements consist of platinum, copper or nickel have a repeatable resistance versus temperature relationship, that is R versus T. Consistency, reliability is there. The changes in resistance with the change in temperature is reliable here in this case. Typical application. R versus T relationship is defined as the amount of resistance change of the sensor per degree temperature change. Same definition of R versus T relationship. See, in this, the main focus point is the relative change in resistance. The change in resistance with change in temperature, it varies slightly over the useful range of the sensor. The variation is very slight in the useful range of the sensor. So these RTDs, resistance temperature detectors, are replacing the use of thermocouples. As I told the disadvantage of thermocouple earlier, small variation in temperature cannot be measured, whereas here using RTDs, even slightest change in temperature can be measured. So thermocouples are gradually getting replaced with RTDs, particularly in temperature applications below 600 degrees due to higher accuracy and repeatability. When we say accuracy, the variation of resistance with variation of temperature. Repeatability, the same variation for the same variation in temperature. Same variation in resistance for the same variation in temperature, repeatedly done. It doesn't change with time. Typical drawing, typical diagram of an RTD. A wire wound platinum resistance thermometer, it looks like this. It is encapsulated. Inside you will have a platinum wire. That wire platinum is sensitive to changes in temperature, and that changes in temperature will result in change in resistance, which can be measured in these two ends of the wire. So this end is connected to the processing device, to the electronics, which converts this change in resistance to changes in temperature and indicate the changes in temperature. That is how it is applied. RTD application, you must be clear. More or less, it's the thermistor only. The concept of thermistor applied in a practical manner. You get the device RTD. In the syllabus, I think RTD is there, and this is a device which is used to measure temperatures in your profession also. You can come across an RTD based device, or you can come across a temperature measuring device which uses a resistance temperature detector. Right. Next one is very interesting and an important topic also. widely used application, strain gauge. What it is? It is a gauge which makes use of the physical property of electrical conductance and it depends on the conductor's geometry. What does it mean? When we say physical property, it is length and cross-section area. We saw it when we were discussing the Ohm's law. We saw that rho L by R equal to rho L by A is the concept that we discussed. We will see that here again. When an electrical conductor is stretched within the limits of its elasticity. So we are linking up with this material science now. We discuss the properties of materials, elasticity. When we are discussing elasticity, this was in workshop technology. So what is elasticity? What are the elastic limits? That means when we subject a material to either compressive or tensile forces, up to a certain limit, they stretch or get compressed, and when the forces are removed, they get back to their original shape and size. That principle is very much applied in the strain gauge. That is what it is described here. When an electrical conductor is stretched within the limits of its elasticity, such that it does not break or permanently deform, that is, doesn't reach its plastic limits. It will become narrower and longer. When we stretch the conductor, it becomes narrower and longer, as you can probably relate it with our video when we discuss the tensile test. Changes that increase its electrical resistance end to end. It becomes longer, narrower and longer, and that results in change, which results in increase in resistance. That is, when we apply R equal to rho into L by A. What happens when we stretch the material? L increases, A decreases. Longer, L is longer, A is narrower. So when the material is stretched, I repeat, the length increases, area decreases. Both are complementing each other, and when we apply the formula R equal to rho L by A, rho is resistivity of the material that is used, length and area. So that equation we apply. Length is increasing, area is decreasing, they complement each other, and the resistance value will increase significantly when we apply this kind of forces. And as long as they are in elastic limits, when the forces are applied, the resistance changes, and when the forces are removed, the resistance gets back to its original value. Because the material also comes back to its original value. The length also reduces, area will become more, rho L by A will result in reduced resistance. This is the basic concept, a very important concept, a widely used application of strain gauge. Conceptually, you must be very clear. Similar, the other side of it, when a conductor is compressed, such that it does not buckle, will bend off fully or break, it will broaden, area increases, length decreases. When we compress the same material, again the rho L by A principle is applied, that results in decreasing resistance. You can think it. So both, when we pull, the resistance increases, when we press, the resistance decreases. That's the concept of the strain gauge. From the measured electrical strain gauge, the amount of induced stress may be inferred. So by this measuring changes in resistance, we can identify the amount of forces that are acting on the particular area or a particular place. That is the typical application of a strain gauge. Construction-wise, typical strain gauge arranges a long, thin conductive strip in a zigzag pattern of parallel lines. Small amount of stress in the direction of the orientation of the parallel lines results in a multiplicatively larger strain machine, because we are increasing the length by arranging in a zigzag fashion. I'll show the diagram also, how it goes. We'll see the diagram also. And the multiplicatively larger change in the resistance characteristic observed with a single straight line transmission. You can have a larger change in the resistance by using a longer wire. In a small area, small place. When we use a longer wire in small place, we are orienting it in a zigzag fashion. We'll see the diagram. These are the two ends of the wire. This is the wire, you can see zigzag manner, closely arranged in the zigzag fashion. You can see the total length is the length of this wire, full. And the cross-sectional area is individual cross-sectional area of this wire. So when we subject it to forces this way, tensile force, when we pull this apart, what happens? The length, individually the length will increase and the area decreases. Elastic limits, so when you remove these forces, it gets stuck. The diagram here is a typical oil strain gauge. The gauge is far more sensitive to strain in the vertical direction. You see, it is very sensitive in this direction, not very much in this direction. The market subject active area helps to align the gauge very easily. When we are installing, so when we are using this strain gauge, we must orient it in such a way that the forces are acting in this direction of the gauge, not in this direction. Because the response is more in that stretching the gauge in this direction. Typical application of strain gauges, what are called as load cells. I'll explain them further. Pressure sensors, the concept is used in pressure sensors. Very much used, so you will be able to get it clearly. Before that, we will see the demo of a strain gauge and then I will get back to the application.
Okay, this video is for experiment number 5, strain gauges. Basically, this experiment uses a Wheatstone bridge, which I have already constructed here. Wheatstone bridge consisting of 2 resistors, along with on one side of the bridge, one side of the bridge has 2 resistors, and the other side of the bridge we have a variable resistor or a potentiometer.
It's a potentiometer, typical application of discussed earlier, voltage divider circuits. Typical application of voltage divider circuits is applied here, you can see. These 2 resistors form the Wheatstone bridge. I am not discussing the Wheatstone bridge here. Concept probably will be knowing, balancing the resistors between the arms results in a residual current, and the current balancing is done using the Wheatstone bridge. I will not discuss that Wheatstone bridge in detail. It's not part of the syllabus also.
As one resistor, and then the other resistor being the strain gauge. So the Wheatstone bridge consists of 4 resistors. On one side of the quote-unquote one side of the bridge are 2 standard resistors, and then the other side of the bridge consists of the strain gauge, which is an effect of variable resistors because the resistance of the strain gauge changes as strain is imposed on it, and then a variable resistor here to balance out the bridge. Connected to our Wheatstone bridge is a DC voltage source set to 15 volts, and then a digital multimeter set to volts to measure the difference in voltage output coming from the Wheatstone bridge as it gets put out of balance based on the increased resistance of the strain gauge. Strain gauge is attached to what will be a cantilever beam.
See, this is the actually practical system. The wires are arranged in zigzag pattern here. You can probably closely watch. It is like this, the wires are arranged. The 2 ends are here. In between, in this strain gauge, lots of zigzag arrangement of the wires is there, and this is fixed rigidly onto this bar. This is attached using adhesive, firmly attached, so that the forces will act in this direction. You can see the video, it explains further.
Basically, it's a hollow aluminum beam. Strain gauge is attached to it, and the beam is attached to the table to simulate a cantilever beam. What you are to do is balance the bridge out. So right now, as you can see, it's set to about 0.8 volts. It's unbalanced by 0.8 volts. Right now, what I am doing is that I am turning the resistance here from the potentiometer
Is balancing
to
the
try to level out this bridge as much as possible. So right now, it's down to about 6.7 millivolts, which is as close to zero as I'm going to get it. Once you have that done, you should see something similar to this hook with a base to it. And what you can do to the base is attach weights to increase the force being pulled down on the cantilever beam as you hang this hook from the edge. So the procedure for getting your voltage readings are as follows. You'll first push null on the digital multimeter. You can tell that zeroes it out. Then take this hook it to the end of the cantilever beam, making sure that it doesn't swing too much. You'll see an increase in voltage. You can see that the voltage went up to 0.4 millivolts. Now, as you can tell, it drifts a lot. It's already up to 0.6. So what you're going to have to do your best is to put the weight on and then take your reading as quickly as possible to avoid the effects of the drift. Then after you take your reading, remove the weight, unnull, go ahead and take another kilogram weight, put on the hook, so now you have 2 kilograms attached to the hook. Null it again, and go ahead and hang the weight. See the resistance increase again. Take that number, remove the weight, unnull, and keep repeating that effect until you have hung up the full 5 kilograms worth of weight plus the hook to the cantilever. So that concludes the instructional video for experiment number 5, strain gauges.
A typical application of a strain gauge and demonstrating the concept. So in the video you could see when the weight is hung on the cantilever beam, the beam bends, and that bending is sensed by the strain gauge. The bending happens exactly at the place where the strain gauge was mounted. So it is pulled down here and here at these ends, particularly at this end. When we look into the video, it is at this end, it is getting pulled down, so that pulling down itself acts as a stretching force on this particular wires, the zigzag wires which are arranged. So the total length will increase, cross-sectional area because of the stretch will decrease. I repeat, R equal to L by A formula is applied, and R will increase because L is increasing and A is decreasing. They result in increase in resistance. That increase in resistance that will be converted into measurement of force. Can you think of a typical application? Looking at this concept, just to apply your common thinking, common application, and come out where you can think that a strain gauge is used. A wild guess. You may be right or wrong, I don't mind that. I want you to have a wild guess where this concept can be used. Then I will tell the place where it is most commonly used also. You will be able to appreciate it. I want to know whether you or any one of you will be able to come out with the same thinking I am thinking. Please respond quickly. Either respond with a yes or a no. If you are not able to think of anything, fine, I will continue. If you think, as I was telling you, it may be a wild guess, any typical application where you feel a strain gauge may be used. Now, by now, I think going through the concept, you know that a strain gauge can be used by measuring forces, loads, pressures, and give you the truth. I want you to think of application. Quickly, can you respond? You want a yes or a no? In case you think of something, you write what you are thinking. Otherwise, you say no, sir. You can't. You are not coming across such application. Then we'll continue quickly. So Akash is doing no idea, right? Fine, no problem. How about others? See, why I keep interacting like this is sometimes I get a doubt that my communication with you people is lost and you are not able to hear me or see the slides or see the contents properly. I keep asking you sometimes and your responses will make me comfortable. Got reading also no idea. Akshay has told weighing bridge. Fantastic, Akshay. Very good. Excellent thinking for others also. Weighing bridge is one place where strain gauge is used, and he is bang on my thinking also. How about others? Any other application? Akshay used the same thinking. Think of something that is more simpler, more widely used. Of course, it's not just for Akshay, it's for others also using this clue. Akshay has told it's a weighing bridge. This concept of the weighing bridge is used in a more commercial pattern. Guitar, fantastic. Again, yes, it can be used in a guitar. But Javian, in a guitar, what is that you think you will be measuring? I am not very good at music or musical instruments. I can definitely relate it once you tell your thinking. Yeah, guitar strings, I could get that as guitar strings, but what is the application in guitar strings, the strain gauge application? I want to know your thinking of the strain gauge application. See, what comes to my mind when I try to link it up is the strings when we stretch them or when we trigger them on the guitar, the length definitely varies. Is 7 steps. Ironically, using the concept of and you can perform more if you are better. The voice is breaking. Others. Yeah, it appears then, looks like, again, concept of segregation is something similar to that. If I speak continuously, looks like the network is getting jammed with my continuous talking and the voice starts breaking. Probably I may have to speak a little slowly also. So probably that's another kind of a feedback. When I speak slowly, this voice breaking chances may be less. That you will have to tell me. Whatever I spoke just now, if you felt it was clear, probably it is that. Of course, getting back to the guitar strings, I tend to speak slowly now. I was telling the vibrations of the strings are more important, and the vibrations are dynamically sensed using the concept of the strain gauge in an electric guitar and taken up for amplification and signal processing. Is it that what Jovian was thinking? I just want to know his feedback. That's good. Okay, fine. You are speaking in the same lines. And that may be one of the applications. See, me being an instrumentation guy, I try to relate it to the concepts in each and every application that I come across. Good example, but the more popular one, as Akshay was putting it rightly, weighing bridge, typical appliance that is used in the day-to-day life. What I see across is the small weighing machines that even the vegetable vendors are using nowadays. Every shop, even cart pulling vegetable vendor, they are having digital weighing balances. Every one of you are able to get this particular point. Even on the roadside, a cart pulling vegetable vendor, a fruit vendor, every shop more or less, they are using digital weighing scales. One very excellent example of application of the strain gauge. In most of these devices, the inside sensor which senses the variation in weight and thereby measures the weight will be a strain gauge. Please remember that. Again, academic point of view, exam point of view, this is a very important topic. Probably one in every 3 papers or so at least. You can expect one or the other question on strain gauge. And generally it is at either 5.5 marks levels or 10 marks levels. Working principle of a strain gauge, applications, etc. As you saw in the video, in the weighing balance also, what they can do is they apply the strain gauge onto one rod, let's say, and on that they will have this weighing platform. The rod is connected to the weighing platform, and whenever the weight is applied, that weight is transferred to the rod on which the strain gauge is mounted. So the variation takes place in the strain gauge's resistance, and that resistance variation is converted into voltage and then converted into digital indication of the weight. Again, these As Akshay was telling, weighing bridge, that is, weighing bridge is used for measuring very heavy weights. Small weighing balances are used for measuring lower weights. But the concept of application of strain gauge, they remain the same. The material that is used wherein the strain gauge is mounted in a weighing bridge and in a weighing balance commercially, small weights weighing balance, the material used may be different. The structure may be different. Is my explanation clear? Typical application is in what they call as the pressure sensor or the load sensor. That is what the typical application is here. Load cell is a device which uses the strain gauge, as I explained you now, in measuring the load, the weight. The weight can be applied in this direction. The strain gauge will be mounted in this direction. In the pressure sensor also the same way, the pressure can be measured. The container on which we need to measure the pressure would have the strain gauge fixed on the container. So the expansion of the container can give an indication of the pressure that is required to be measured. Important topic. Hope it is clear. Good. We'll go to the next topic. A small one, typical application of resistance, change in resistance again. It's in the light dependent resistor, LDR for short. What it is? This is a simple light dependent resistor or a photoresistor which you people would have come across. Is a light controlled variable resistor. Principle of operation is when the light falls on this resistor, the resistance changes. It's generally made up of a semiconductor device. The details we'll be seeing in Unit 4, semiconductors. For now, photoresistor is made of a high resistance semiconductor. The material used is a semiconductor material. Resistance of the photoresistor decreases with increasing incident of light intensity. Higher the intensity of light impinging or falling on this material, the resistance will decrease. And that decrease in resistance will indicate the level of light intensity. In the dark, a photoresistor can have a resistance as high as several megohms, while in the light, when it is subject to light, the photoresistor can have a resistance as few hundred ohms. From megohms to 100 ohms, it can change with light. Typical application by now, I think you would have imagined. It can be applied in light sensitive detector circuits and light in dark activated switching. So light activated switches, they are again one of the most common applications nowadays. Behind every such device is an LDR, a light dependent resistance, or the concept of LDR is applied in all these light sensitive switches, which I think most of us would have come across here and there. Can you think of a typical application before we close?